last class, we talked about the rest of the types of radioactivity that we'll be talking about for this class, and a little bit about their behavior, ending on this slide, showing the kinetics of radioactive decay. All of the decay plots are going to look something like this because they all follow first-order decay. The y-axis will have a different scale, the x-axis will have a different scale, different units, whatever. But if you scale them correctly, they should all basically look like this plot. And this is just a bunch of nuclides and their half-lives. That might be helpful for you for homework questions, for example. Moving on to the more interesting stuff. This is stuff that we didn't do in 3A, or you didn't do in 3A probably. Integrated rate law, using some of the kinetic stuff that we've done before. Since all of our nuclear decays, all of our radioactive decays are first order, all decay is first order, radioactive decay that is. Since they're all first order, we can use the integrated rate law for the first order reaction. And we get this, natural log of the concentration at time, T, over the concentration at time equals 0, the initial time, equals the negative K, that's our rate constant, times whatever the time is. So we can work in partial half-lives, is basically what we're getting to here. In 3A, in previous chemistry classes, at least my chemistry classes, we've only been able to work in, we are either at a complete half-life, so 1, 2, 3, 4, 5 half-lives, whatever, or we could say we're between half-life 2 and 3, and so we'd be between these sort of time zones. With this first-order integrated rate law, we can say we are at this exact amount of time, or at this time we are at this exact concentration, stuff that's in between half-lives, which is great. And it's stuff that we've done before. We did this in the kinetics chapter. The problems are going to be set up a little bit differently, but the equation is the same. And then for these, you will also need this. We saw this, I think, last class. The half-life is equal to the natural log of 2 over K. This is how we find, usually, how we find the K for our integrated rate law. So they're related. For radioactive decay, you can substitute in concentration or substitute concentration in nuclei. You can also use mass. For those ends instead. These are all things that are proportional to each other. Mass, concentration, number of nuclei. They're all related. They would have the same conversion factor to switch between them. You'd apply it to the top and the bottom, and so they would cancel out. So you can use any of those three. Let's say that we have plutonium-236. Plutonium-236 is an alpha emitter with a half-life of 2.86 years. We want to know how long, so we're looking for time. Will it take, for a 1.35 milligram sample of plutonium, to decay to 0.100 milligrams of the same thing? Our relevant equations, natural log concentration at time t over concentration at time equals 0 equals negative kt, and t1/2 equals the natural log of 2, if I'm remembering correctly, over k. I'll give you a little bit of time to give that a shot. All right. We have a half-life that was given to us. The half-life is where I'm choosing to start, because for our integrated first-order rate law equation, we need the time at T, or sorry, the concentration at T. That's going to be this 0.100 milligrams. We need the initial concentration, or the initial amount. That's going to be this 1.35 milligrams. That's how much we started with. We are trying to find T, so I'll underline that. And we do not have K. So we've got almost everything that we need to solve the integrated first-order rate law problem. We don't have K. K shows up in our T1/2 equation. Our T1/2, our half-life, is 2.86 years. It's a relatively simple matter to convert this to solve for K. K equals 0.693 over T1/2, which is 2.86 years. So our K is 0.24 ... inverse years. Now that we've got our K, we can plug into our integrated first-order rate law problem. So I'm going to do natural log of 0.100 over 1.35. Natural log 0.1 divided by 1.35. The units cancel. This is negative 2.60 and some other stuff with no units. And this is equal to negative KT. Then we divide both sides by negative K. Negative K being negative 0.24 ... inverse years. I'll leave it as negative K on the right side so it cancels. And we're left with T equals negative 2.6 ... over negative 0.24 ... inverse years. The inverse years will hop up to the top, so we'll get an answer in years. And it should be 10.7 years. Questions? As mentioned previously off the recording, we can get kind of like a rough estimate of if we're correct, do a ballpark calculation of how long it's going to take 1.35 milligrams to decay to 0.100 milligrams. We just want to figure out approximately how many half-lives. So divide by 2. Divide by 2. Divide by 2 again, until we're kind of in the ballpark of the number that we've got. And let's divide by 2 one more time. And we get to 0.084 and some change milligrams. That is 1, 2, 3, 4 half-lives. So we should expect our answer to be somewhere in the range of 4 half-lives. 10.7 over 2.86. About 3.74 half-lives. That's in the order of, in the vicinity of 4 half-lives. So this is an answer that makes sense to us. So that would be a way to check. You don't necessarily have to check if you're just confident that you did it correctly. As we did on the previous example, you can use mass instead of the number of nuclei because of the ratio that shows up in the problem. Rate is also directly proportional to the number of nuclei. So you could also use that instead. I don't think we have an example of that. So there's a calculation. Another thing that we can do with radioactivity, and knowing that radioactive decay is first order, is you can use radioactivity to measure the age of fossils and artifacts. And you've probably heard of this. There's radiometric dating, which is just like the general term, I think. The metric means measuring or relating to measuring, radio being radioactivity. So using radioactivity to measure our date or our time. Radiocarbon dating is the one that you've probably heard about, or just carbon dating, devised by William Libby in the 40s, late 40s. It makes use of the radioactive signature of carbon-14 in the environment. We'll talk a little bit more about this. So one example of this is the Dead Sea Scrolls. I'm sure there's lots of other good examples, but this is the one that's in our book. In the same time frame that Libby came up with radiocarbon dating, some shepherds around the Dead Sea found some scrolls that had been stuffed into jars in a cave. That's why they're called the Dead Sea Scrolls, as they were near the Dead Sea. And they determined approximately the age of these scrolls with radiocarbon dating, and they were discovered to be something like 2,000 years old for little fractions of the Hebrew Bible. The way that radiocarbon dating works, which is more important, is that carbon-14, which is unstable, carbon-14 is unstable. It's constantly being formed in our upper atmosphere because the atmosphere blocks a lot of radiation from coming and getting us and giving us as much cancer as it wants. So up in the upper atmosphere, there's lots of radiation going on because it hasn't been stopped by our atmosphere. And that can include neutron bombardment of nitrogen. So the way that that works is regular old nitrogen floating around in our upper atmosphere, possibly by itself, gets hit by a neutron from space and splits into carbon-14 and regular old hydrogen. Over a long period of time, carbon-14 can decay back to nitrogen by emission of a beta particle, an electron, and it's got a half-life of 5,730 years. Since it's being constantly formed in our upper atmosphere, that eventually makes its way down to us. And since it's constantly being formed and decayed, there's an equilibrium that gets established over the course of thousands and thousands and millions of years. And so the atmospheric amount of carbon-14 is constant-ish. There's like a little bit of up and down, but it's kind of in the same ballpark all the time throughout the history of the world. That carbon-14 can be oxidized into carbon dioxide. Plants uptake this CO2, where this carbon is C14. because it's just out in the environment. And so that'll eventually make its way up the food chain, since pretty much everything eats plants or eats things that eat plants. And so all living organisms contain approximately the same ratio of C14 to C12 that's found in the atmosphere. And then when you die, one of the things that happens is you stop eating. Once you die, that's the last of eating that you get to do. And because you're not eating anymore, no more C14 is absorbed or taken in, put into your body. So C14, the amount that you have in your body drops, or the amount that any living organism has in its body drops over time after it stops taking in new carbon.
Is C14 the reason why it's not ideal for astronauts to be in space for that long?
C14 is not the reason that it's bad to be in space for a long time. It's gravity. Lack of gravity, I think, is like the main reason why you don't want to be in space for too long, because it affects your bone density. So like it can lead to pretty serious long-term health effects. There is a lot of issues with radiation, but that's mostly solved with or mostly taken care of with, radiation shielding on ships and astronaut suits and stuff. The approximate maximum age that can be estimated with radiocarbon dating that's usually cited is 50,000 years. I don't have any evidence to dispute that number of years. Basically, it's like something like 9 half-lives. Let's get a better number. Yeah, it's a little shy of 9 half-lives. And 2 to the 9th power, it's a decrease of about 512. So you've got about a 500th of the amount as you initially had after this period of time. And if you didn't start with very much, which I'm guessing is probably the case, if you didn't start with very much, decreasing the amount that you have by a factor of 500 means that you've got even less, and that makes it harder to check. So that's this bit about it's too low to measure accurately. The rule of thumb that I learned is that after about 10 half-lives, you've basically got no more radiation. Regardless of how much you had to start, after 10 half-lives, it's basically all gone. And so this lines up with approximately 10 half-lives. To figure out how accurate our radiocarbon dating is, since there's a little bit of plus or minus to the carbon in the atmosphere, it can be checked against ages that are known from historical sources. So this can't be done just by itself. There should be some validation with other things that we know are like, we've got in the historical records, people wrote about like, oh, this thing was constructed around this time, let's check the carbon levels for that thing. Or let's take ice cores from super deep down into the earth and figure out what the concentration of C14 in the atmosphere was over that time. So there's a deviation of like 5% in the carbon-14 levels, right? So there's a little bit of plus or minus. It's not completely exact, but you can make corrections using data from bristlecone pine trees or other old things that we can check the age of. Let's say that a researcher claims that an ancient scroll originated from Greek scholars in about 500 BC. 500 BC. A measure of its carbon-14 decay gives a value that's 89% of that found in living organisms. We want to know how old is the scroll and could it be authentic? our T1/2 for carbon-14, 5,730 years. Some other things that we've seen today, T1/2, 0.693 over K, and natural log of, let's use N this time, the number of nuclides that we have at time t over the number of nuclides at time 0 is equal to negative KT. So the first question that we're answering is how old is the scroll? So we are finding T in our first order integrated rate law equation, finding this T. That means that we need to know what the number of nuclides is, and we need to know what K is. Let's start with finding K since we've already practiced doing that. So K is 0.693 divided by the half-life. So 0.693 divided by 5,730.
How did we get the 5,730 years?
We would have looked up the half-life. We saw it in an earlier slide. So 1.2 dot 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 times 10 to the minus 4 inverse years. Our K value. Okay, so we've got K. We need to figure out what our NT and our N0 are, or N0 are. Any ideas?
Would our N naught be the 500 BC, and then our N2 would be 89% of that?
So we're looking for things that have the same units. 500 BC would be a period of time. 89% would be an amount of like
Can we not
the element.
What the 89% of 500 BC is? Or no?
We convert 500 BC?
One of those is a time and the other one is like a number of things.
Would it be 0 and 500 then?
It's not 0 and 500.
500.
N is standing in for the number of nuclides. One of them is 89%. So this is part of what makes these questions tricky. Otherwise, they're not tricky. It's just like figuring out what the numbers are. That's like, I think, the only tricky part. So at time t, 89% remains. All right, that's what we're saying. We are at time t, or we are t years in the future, and we've got 89% or whatever from when it stopped absorbing new material, this scroll.
So would it not be 100 then?
So would it be 11%?
Never been.
So the 89% is what I would set as the NT. What amount, if we have 89% now, what would we have had initially? 100%. So initially we had, and by we had I mean the scroll had, 100%. So 89% will go in this NT spot, 100% goes in the N0 spot. So natural log of 89 over 100, also over negative K, if we wanted to do it all in one step, equals T. So natural log 0.89 divided by negative K. The time value is 964 years. So this scroll, by our radiocarbon dating, is about 964 years old. This answers the first part, how old is the scroll?
Do we cancel out the negative, or like, do we just assume it's positive?
If you enter natural log 89 over 100, you should get a negative number. So the scroll is 964 years old. That's the first part of the question. Second part of the question, could it be authentic?
Yes, because it's less than 50,000. You said it has to be.
The scroll is claimed to be from 500 BC. How many years ago is 500 BC?
Like, yeah,
That's like 2,500 years ago. So the claim is that it's 2,500 years old. The radiocarbon dating says it's about 1,000 years old. The plus or minus on radiocarbon dating is about 5%. We are way over 5% off. If it was like off by 10 years and we're 1,000 years old, like, okay, that seems, that might be reasonable. You know, there's a little bit of inaccuracy, not 100% precise, but this is way different. So definitely not authentic. $2,500 years is not the same as 964 years. If they claimed that it was from 1,000 or from the year 1,000, that's like roughly 5% from 964, kind of in the ballpark. That would be reasonable enough. But this is way too old that they're claiming it is. So if this was like an actual thing that happened, what they probably did is they found some really old paper and then made a forgery or something. That's usually how people would get past like radiocarbon dating tests. You find paper from about the same time, you make your forgery on that with like old ink, maybe you age the ink. It's a whole thing. Again, radiocarbon dating is limited to objects that were both once alive. So a scroll makes sense because it would have been made from either animal product or from like a plant, papyrus or something, or a tree or other pulp. So it would have been alive at some point and probably pretty recently to when it was made. And we're also limited to things that are less than about 50,000 years old. If we want to work with things that are not alive, like rocks, then we can use the ratio of uranium-238 to lead-206 as a measure of time. This works for igneous rocks, which I think are from volcanoes or from lava. Something like that. I'm not a geologist. So uranium-238 decays to lead-206 with a half-life of 4.5 times 10 to the 9 years. 4.5 billion years. So that'll last a lot longer. We can get much better results from that. And the reason that this is important is that lead that results from radioactive decay has a different isotopic composition different isotopes or different ratio of isotopes present compared to just regular lead that we would expect to find in the environment. So looking at the specific isotopes of lead, using like a mass spectrometer or something, we can figure out how much of the lead is this different isotope. And there's probably also still some uranium in there, and we can compare that ratio. Let's say that we want to use this method to estimate the age of a rock. A rock, not the country, contains a lead-206 to uranium-238 mass ratio of 0.145 to 1, assuming the rock did not contain any lead at the time of its formation, lead-206, determine its age. Yeah, so we need a couple of pieces of information. Our half-life, 4.5 times 10 to the 9 years. We're going to be using the same other equations. Nt over N naught equals negative KT, and T1/2 equals 0.693 over K. So just like with the previous problem, a thing that we can do to start is finding K. That's arguably the most straightforward part of this problem. So we can find K. K is 0.693 over 4.5 times 10 to the 9 years. Which is 1.54 times 10 to the minus 10 inverse years. We are again finding age, which is time. That means that we need to figure out what is NT and what is N naught.
I tried 0.145 over 0, but N naught is 0, but you can't do that. So you have to do the
You wouldn't have started with 0.
Wouldn't N naught be 1?
N naught is not 1. Unfortunately for us, this problem does basically work out if you just put in this 0.145 for NT and 1 for N naught. That's not the correct solution to this problem.
Okay.
So that's why I'm saying it's unfortunate that it works, because it's not correct to do it that way. So at some time, whatever amount of, all right, let's start with figuring out the initial amount that we have. Let's say that this ratio, since it's a ratio, we can choose any amount that we want. Let's say that we've got, that this 1 is actually 1 gram and this 0.145 is 1 gram, because it's a mass ratio. So that 1 is the uranium-238, and the 0.145 is the lead-206. So we're going to assume 0.145 grams Pb206 and also 1.00 grams of uranium-238. Actually, it doesn't work if you put that 0.145. It works if you subtract the 0.145 from the 1. Anyway, the correct way to do it. Right, so we have, at this point in time, 1 gram of uranium-238. This would be our NT. It's the amount that we have now. To find out the initial amount that we had, we're going to use this 0.145 grams of lead-206. this came from uranium-238. How much uranium-238 in terms of mass would that have been initially? It's the question we're trying to ask. So 0.145 grams, Pb206. What's the mass of lead-206? It's the molar mass. Specifically for lead-206, not the lead that we have on the periodic table. It's 206. I have to make you think a little bit there, right? So we can calculate the number of moles of lead-206 that we have. I'm guessing that most people aren't doing this all in one step, in one fell swoop. So I will not do it that way either this one time. How many lead-206s are produced from each uranium-238? What's our ratio?
0.145
When uranium-238 decays to form lead-206, how many uranium-238s go in? How many lead-206s come out?
Do we just divide the 1 by 0.145?
It's just a 1-to-1 ratio. So we're talking about nuclides, little nucleuses, right? A lead-206 is formed from uranium-238. There's some other decay processes that go on. There's probably a long chain of events to get from this U-238 to the lead-206. We're not breaking our uranium into 2 different nucleuses though. We don't have enough mass to do that. So it's just going to be 1-to-1. So for every 1 lead-206 that we have now, that's this number on the bottom, we would have had initially 1 uranium-238 to start with. So that's going to be the same number. That means that we've lost this many moles, lost or decayed this much uranium-238. We need to get this back into grams, because grams is the amount that we have for our U-238 that we've decided is our NT. How do we convert moles to grams? Times it by molar mass. What's the molar mass of uranium-238? It's 238. And I'll cross this out in a different color. Purple shows up well enough. Okay, so that 0.000, however many zeros it is, 7 times 238, 0.1675 ... grams of uranium-238. So what's our initial amount of uranium-238? Is it 0.1675 grams? It's not. You have to add it. Okay, so our N naught is 1.1675 ... grams. So what we were calculating here, we initially had no lead-206. That lead-206 entirely came from uranium-238. That means if we can figure out how much uranium-238 it took to make this amount of lead-206, we can figure out how much uranium-238 we lost. So that's what we did this whole bottom line calculation for. Calculating back to the amount of uranium-238, we discovered that it was about 0.1675 grams of uranium-238. That's the amount of uranium-238 that decayed to form the lead-206 that we have. So we have to add this amount of this 0.1675 grams to the amount that we have now at whatever time t is. That's why we get 1 plus 0.1675. You could have also chosen to not use 1 and 0.145. You could have decided that we had 100 or 1,000 or 5 or 7 grams of whatever our mass ratio was. I think it's easier to just use the numbers that are in the mass ratio. And that's how we get our N naught. Now we've got N naught, we've got N naught, we've got NT, we've got K. It's time. Because that's T's time. Ha. So we can put in T equals natural log of 1.00 grams over 1.167 ... grams over negative 1.54 times 10 to the minus 10 inverse years. We'll get a value out with units of years. And it's big number. That many years.
Take 1 to the power of 9, right?
So a little over 1 billion years. Which makes sense. We're less than a half-life by quite a bit. So we would expect to be less than 4.5 billion years. And if I remember correctly, the answer is, 1.0 times 10 to the 9 years. Questions? It looks a lot simpler than it is.
Mm-hmm.
The reason that I said unfortunately earlier, if you put in here, this little bit down here, if you put in 1 for the initial amount and 1 minus 0.145 for the time t amount, I think when I put that in, I got the same answer. It's not the exact same number, but it rounded to the same number, which is unfortunate because that's not correct.
Yeah.
So it would work because the number is that big, not because it's correct.
It's close enough to round to the same answer because we don't have particularly precise numbers. Like the answer being 1.0 times 10 to the 9 years. Like the actual number that you get out is 1.02 times 10 to the 9 after rounding. It's like a different number. It's very close because we haven't changed our ratio too terribly much. It's 0.145 to 1. If that 0.145 were bigger, then that would probably make a bigger difference. And then also because these are really large masses, even though they're different by like 32. 32 is like less than a sixth of their total mass, and so they're relatively close. So it kind of turns into this rounding error situation. Anyway, don't do it that way. Do it the correct way. Just erase that. Put my number cover back on. Questions about that problem? Boy, wouldn't that be a fun one to have on a short answer problem.
That better not be multiple choice.
Yeah, that'd be a fun multiple choice one, wouldn't it? Answer be 1.01 times 10 to the 9, but then 1.02 times 10 to the 9 is also there.
That'd be a good free answer question.
That'd be good.
I'm gonna start bringing up points. Those type of questions are hard.
The thing that makes that problem difficult is the ratio. It's the ratio part that makes it difficult.
Could we have done it using PB206 or no, instead of the uranium? That's where my mind was going. Because I thought, like, since we use the PB's half-life, we would have to use the PB's like grams or something.
There might be a way where you could do it with PB206. I don't know how to do that off the top of my head. Because your initial amount would be 0.
That's what
And you're not going to be able to get any ratio to work if you've got a 0 in there.
So just assume 0 for the other.
You would have to use a different formula, I think. Radiometric techniques, radio dating, has been widely used to measure the age of rocks on Earth. So rocks with ages more than 3.5 billion years old have been found on every continent, with the oldest being about 4 billion years old. Presumably, the Earth must be at least as old as its rocks. The Earth must have been here before the rocks. I guess the idea is. Makes sense to me. There are also meteorites that have struck the Earth that are estimated to be about 4.5 billion years old, and those are assumed to have formed at the same time as our solar system. So, according to the book at least, our best estimate for the age of the Earth is 4.5 billion years. So 1 half-life for the lead, or the uranium-238. And then the universe, probably by other dating means, is estimated to be 13.7 billion years old. Other stuff related to radioactivity. We still have 40 slides left, but we'll talk about fission and other fun stuff. In the mid-1930s, Enrico Fermi, a famous physicist, attempted to synthesize a new element by bombarding uranium with neutrons. And the theory is that you could put a neutron, if you bombard it enough, eventually maybe one of those neutrons would stick, and then that would bump up your mass number, and then it might decay by beta decay, and so it would convert that new neutron into a proton, moving it 1 spot up on the periodic table, or 1 spot over. And it sort of worked. He detected beta emission, which is what he was expecting to see, but he never checked or didn't examine the products to make sure that it was actually a new element. So spoiler alert, it's not a new element. Others also repeated Fermi's experiment. Lise Meitner, Fritz Strassmann, and Otto Hahn. This is Lise Meitner, after whom is named meitnerium, I think, on the periodic table. They found that the products contained several elements that were lighter than uranium, meaning that it was not a new element. And their discovery changed things. In 1939, they reported that neutron bombardment of uranium resulted in nuclear fission. Fission is splitting. So rather than incorporating that neutron into the nucleus, doing beta decay and bumping up 1 spot on the periodic table, they hit the nucleus with the neutron, and it broke the neutron, or broke the nucleus into pieces, which is what the fission part of it was. And as part of that splitting, there was beta decay that went on, which is what Fermi observed. So it split into 3 elements: barium, krypton, 3 neutrons, and lots of energy. I'm pretty sure this only works with uranium-235. It doesn't really work with uranium-238. That's the most common isotope, but it's this U-235 that actually undergoes fission. So you can bombard it with a neutron. It breaks and then produces a lot of energy. Notably, it also produces 3 neutrons. That's very important for the fission process. Uranium-235, if you've got an enriched sample, can undergo a chain reaction. So those neutrons that I was talking about, those neutrons from one fission event can cause other fission events. I don't know if that's what they're technically called. And that's the chain reaction part. So we do one fission, it breaks and releases 3 really high energy neutrons. Those can go to hit other uranium-235 samples that undergo fission, and so on and so forth. This doesn't work if you don't have a lot of uranium-235, because other things will get hit by those neutrons, and you just don't have enough for it to go nuclear. So you need a certain amount of uranium-235 for this reaction to be self-sustaining. And if you do have enough, then you can make an atomic bomb. And I'm not a historian, so I don't know if these slides are accurate or propaganda or whatever, so take them with a grain of salt maybe. But this is what the book says. So fearing that Nazi Germany would develop a bomb based on nuclear fission, US scientists persuaded Albert Einstein to write a letter to President Franklin, and they started the Manhattan Project over in Los Alamos with the goal of building an atomic bomb. And they detonated the first nuclear weapon in 1945 at a test site in New Mexico. There have been thousands of other atomic bombs that have been set off, just most of them not around people. And the equivalent force was apparently 18,000 tons of dynamite. Germany had already surrendered at this point, but the United States decided to go ahead and drop 2 bombs on a bunch of civilians in Japan anyway and kill something to the order of 200,000 people and leave a lot of radioactivity around them. So that's like the dark side of nuclear. You can also use fission to generate electricity, which is the good side of nuclear. So if you don't just let that fission reaction go crazy, go nuclear, if you control that fission reaction, you can generate a lot of electricity since there's tons of energy that's released. There's no air pollution, there's no greenhouse gases. Really, the only downsides are if you did not build your plant correctly and or you have incompetent workers or people are making mistakes, you've got bad engineering controls in place, then you can get like nuclear plants exploding or melting down, which is obviously not good. There's also some nuclear waste that's generated, some nuclear/radioactive radioactive waste generated, with the very big upside being no air pollution, no greenhouse gases. In the US, since we're scared of radioactivity, historically, we've generated up to about 20% of our electricity from nuclear fission. You also need a source of water, typically, with fission or nuclear. But other countries that aren't as scared have gone up to 70%. That number might even be higher in some parts of Europe. Europe is generally less scared of nuclear and radioactivity just in general. There's ways to use radioactivity to like sanitize produce. So you don't have to apply any pesticides and you can kill all the insects on there. It doesn't affect your food. We don't use that in the US because people are scared of like radioactive food. In Europe, they're not scared of that. And so they use radioactivity to like clean their produce, basically kill all the insects, prevent spread of infectious diseases and pests. Europe, I think, though, is generally more scared of pesticides. So we use lots of pesticides. They don't use as many. There's trade-offs. The cool bit about uranium is that a small amount, like a pencil-sized cylinder, can apparently power a typical car for 20 years. So if we could get nuclear to work in cars, probably never going to happen. Electric is more likely. You could get your car running for a long time. A coal-burning power plant uses 2 million kilograms of fuel to generate the same power as 50 kilograms of fuel generates in a nuclear plant. So it's also like orders of magnitude different in terms of the amount of fuel that you have to put in. And not all methods of nuclear fission create radioactive or dangerous waste or use dangerous materials. This is what a nuclear power plant might look like, and this is what a nuclear power plant does look like, at least at one point in time, because it's a picture. So generally, the way that it works is you've got fuel rods. Fuel rods have a U-35, and they're sitting next to each other. Those are going to undergo decay events. That'll produce that heat, and it will start that chain reaction going. If you just let it go unchecked, then these rods go supercritical, or whatever you would call it. And then, boom, everything explodes, and that's not what you want. And so there's these control rods that they place in between them. And you can raise and lower those control rods, and that affects the amount of neutrons that are allowed to pass between the fuel rods. So it's basically an off-on switch with varying degrees of control. If you raise the control rods, the reaction goes faster. If you lower the control rods, the reaction shuts down. One of the ways that at least one nuclear plant has melted down in the past is that their default position for this system, is my understanding, the default position was all the way on. So in the event that something crazy happened, the plant didn't shut itself down, the plant turned itself all the way up. And because of that happening, there was like some electrical, something happened, and that's what caused the nuclear meltdown. I don't know which plant it was. So obviously, right, it seems obvious that you would want, in the event of something bad happening, the control rods drop, everything shuts itself down, no big deal. It seems like a no-brainer. The heat that's generated from this reaction can be used to pressurize water. So you have this tank of like very special water. It takes a very particular kind of water to do this reaction, is what my understanding. You can generate some steam. The steam runs a turbine, and you make electricity. The biggest problem is that they can overheat, not overhear. They don't have ears. Despite some safety precautions. So Chernobyl melted down apparently because of an experiment designed to reduce maintenance costs. Cutting costs, not always a good idea. They disabled some safety features, and the nuclear core overheated, began to burn. There were 31 immediate deaths, and a 32-kilometer radius became uninhabitable. There's also the Fukushima reactor. I was in high school. There was a 9.0 magnitude earthquake that triggered a tsunami, as you would expect in the ocean. And there were lots of things that happened, lots of bad things that happened related to that, but there were no radioactivity-related deaths. There was a significant radiation release, but they were able to shut it down and I think encase it in concrete. Neither of these produced a nuclear detonation because you have to have sufficiently enriched uranium-235 fuel for a nuclear reaction to happen. But people do like to hand-wring and hem and haw about, like, well, what if somebody steals our nuclear fuel and enriches it to make a nuclear bomb? I don't know. Doesn't seem like a problem to me, but it's also not my job. One of the other real problems, though, is the disposal of nuclear waste. It's difficult to store nuclear material, radioactive material. And you do basically just have to store it. You can also, I think you can reuse it, but you have to go through the process of enriching it again, which involves like separating out the ideal isotopes and the not ideal isotopes. And as far as I know, nobody does that. We could do it, but nobody does. They just bury it. They just put it in the ground, and it's just going to be there for billions of years. And I think the biggest issue is that the containers leak. Like, they always leak. Like, you can't stop them from leaking. I think Hank Green has a video about it. There's lots of videos. There's tons of videos about, like, nuclear stuff. People find it fascinating. Where does the energy come from? In our mass reaction, we've got uranium-235 and a neutron. So our total mass, or before mass, is 236 and some change AMUs. We know that there's 3 neutrons, a krypton-93, a barium-140, that come out. If you add all of those up, the after is 235 and change AMUs. Nuclear can convert mass into energy. This is one of the important caveats to the law of conservation of matter. Matter is not actually conserved always, all the time. It's generally conserved, but if you do a nuclear reaction, you can convert mass into energy. And this is based on E equals mc squared. Energy is mass times the speed of light squared. This is Albert Einstein's famous equation. And we'll pick up here next class.